Now it knows where to anchor.
Yep. It's going to, so let me show you the default. So when this runs, the first thing it's going to do is it's going to impose an anchor. It's going to set one of the factor loadings to 1. And let me walk, so let me get all the output to print, and then I'll walk back up through it. Here, I'll bring this back. Actually, it will show it when I...
This is random. Well, I mean, it's related, and I don't know if I missed it. But did you go over what your input file looks like?
This one?
Just anyone in any of your lectures, being like, this is what the input file looks like. So
No, I was just bringing in comma-separated or tab-separated files.
Okay.
And then once it's in, then I save it as a... So you can read those indirectly, and Stata will store the values. And then what I've done then to make our lives easy with the ones that we've done is I've done that beforehand and then just had it save the DTA file.
Okay.
Yeah.
You can see what it looks like if you click on the data browser. Okay. Sounds good. Thanks.
It's very SPSS-like. There's the values, but then there's this additional meta information on all the values. Did you get it, Troy?
Yes.
Okay. All right, so let's walk through the output. So the first thing we notice is it tells us the endogenous variables. As always, our measurement variables are always endogenous. The latent variables are B and M, and the only exogenous variable is the latent variable A. It did a bit of running, didn't like something at the start, so it's giving us a warning, but it figured it out pretty quickly. 766 is our N. We should probably take note of that. In fact, I'm going to write that down because I'm not sure I have that anywhere. So we have 766 results. And now notice what it says here. It gives 3 restrictions. These restrictions are where Stata is telling us what it decided to do. So B1 for B has been set to 1. So this essentially is where it's telling us the anchors. Now, there's ways that we can go in and tell Stata to do other things. And we'll take a look at that eventually, but not today. We'll come back and look at that one. Because there's times when we want to set a different variable as the anchor to make it run nicely, or when we'd actually want to set the variance of the variable to 1 instead of having it anchored to a particular item. All right, so now we can actually talk about the t-test. So the t-test is, so for example, if I want to know, does M actually predict B, my estimated coefficient is 0.89 and change. The standard error is given, a z-score of 18 with a p-value reported at 0.000. Now, of course, we know that means it's really, 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 it's not 0, but it's really, really small. Well, this is interpreted just like a z-test or a t-test. This essentially is saying, yes, that value is statistically significant. Well then, okay, then we've got to remember, well, what actually is the null hypothesis in that case? Well, the null hypothesis is that the parameter, which would technically be beta. Yeah. So the null hypothesis is that beta equals 0. So if I can reject this, which I do, then that tells me that beta does not equal 0. And I can take it one step further, and I've actually got a confidence interval for what the value beta should actually be. Now, I pretty much can do that with every parameter that's been estimated. Some of them make a little more sense than others. So M to B has, in effect, a weight of 0.89. A to M has a weight of 0.81. And then my measurement values also are reported. I'm going to ignore the constants for now. Those are the intercepts, which we're not really concerned about. And my loadings are 1 point. Now, A to A1 was constrained as 1, so there's no statistical information for A1. But A to A2 has 1.06, 0.05 is the standard error, 19.13. So this tells me that the factor loading from A to A2 is statistically significantly different from 0. which we kind of expect.
Are these standardized or unstandardized?
These ones right now are unstandardized. These are unstandardized. All right, so let's scroll down a little further. So we've got our measurement information for A, measurement for B, then M. Now, it even gives it technically gives for the variances, it actually tells us the value, the standard error, and it gives us a confidence interval for the variances. But it could just as well have given us the z-scores. But the hypothesis is that the parameter is 0. But if a variance equals 0, there's no variation. So the assumption is that our variances are always not 0 or greater than 0. So that's why that's not reported. But technically, I could go back and actually ask that question. Other software programs do report that. Stata doesn't. And then at the very bottom, it gives us the LR test of model versus saturated. Chi-squared has 42 degrees of freedom. What did I screw up? I forgot A. Let's go back just for a second to PowerPoint. Oops, don't do that. I forgot the parameters. We have the manifest error variances, the 2 endogenous error variances, 8-factor loadings, 2 yep, we forgot the variance of the exogenous variable. In this case, R5. So we have 24 degrees of freedom, 24 parameters to estimate, so we had 42 degrees of freedom. Sorry about that. Yep, there we go. All right, so we have 42 degrees of freedom. Now, our chi-square is 96.44 on 42 degrees of freedom. The probability of observing that is, well, pretty low. So this means we reject the null. But now in that case, that's actually a bad thing because for this hypothesis test, the null is that sigma equals the sigma implied by the parameter estimates, which we just obtained. That says to reject this, and that's not good because that means that we don't have the right model. Now, we do know that we have the goodness of fit indices that we could go back and look at to see if there's something else we could, another way to justify this. But before we do that, I actually want to look at the modification indices. All right, now, so let's do SEM, standardized. That just takes the output and represents it to us in a standardized form. So again, SEM, standardized. And I just wanted to do that to glance quickly at, so before I go too far, I want to see, before I go too far to see what I need to do with the model, I want to make sure there's nothing strange with any of my predictors. So I would just want to quickly glance at the weights. So for A, the standardized loadings are 0.76, 0.77, 0.71, 0.65. Nothing out of ordinary there. B1, 2, and 3, 8, 8, 8, 8, and 0.66. Okay, that last B3 is a little low. And M1 through 4, 7, 2, 7, 1, 6, 6, and 5, 9. Those are kind of small. Right? But nothing seems out of the ordinary. Everything was significant, so I'm encouraged because when I go back to my chi-squared value, this is not that far off. In fact, really quickly, if I divide 96 by 42 degrees of freedom, I get just a little more than 2. And one of the rules is if the normed chi-square, this divided by the degrees of freedom, is less than 3, then you could argue that you have a good model. All right? So that tells me that, okay, maybe I could do something to justify this to see if there's a connection here.
So you get factor loadings with standardized for the ones that had been anchored before.
Yes, because it's anchored to 1, but you still estimate a variance. So that 1 divided by the variance would be the standardized value. Yeah. Now, it's still technically a fixed value, though. Usually you just report, you usually say that you anchored,
Okay.
and then you report the standardized values. It's very rare that there's any need to report the actual estimates. It's usually the standardized loadings that are reported.
Would you care that at the top with the structure, like above the measuring models, that the A to N coefficient went down somewhat to 0.5?
Well, this just is a standardized value.
Oh.
So again, it's accounting for the variation, the estimated variation for A, which was 0.44. So that's it. We're just seeing. So the value up before was 0.89 and 0.81, but those are unstandardized. So to get a comparison for them, standard deviations to standard deviation, that's a slightly better. Okay. All right, so the next test that I want to look at now is the Lagrange multiplier test. So I'm going to have it report E stat M indices. Okay. This E stat gives the estimated statistics. M indices gives the modification indices. I'll leave it. It's this one. E stat space M indices. Yeah, that just looks like a black dot. Even with it zoomed in. M indices for modification indices. All right, so I'm going to go ahead and click through this. All right, and now let's scroll back up and look at what it's saying. Now, the modification indices, what it will do is it will run the test for every estimated parameter for every parameter that was fixed or constrained. Where constrained is we don't have any constraint. That's where you set one equal to another. I don't have any of those, but what it's doing here is it's estimating every thing that was essentially set to 0 or 1 and saying if you'd freed this up, here's how much your chi-square would have changed. Now, notice it does give a p-value. It does give a p-value. So this is my modification index. And if I notice, my degrees of freedom down the column are all 1. Don't even know why it reports it. Because this is a univariate assessment. And what it's doing is it's essentially saying, if I estimate this one parameter, that's a new parameter I'm estimating, so my degree of freedom for my new model will be 1 less than my previous model. When we do model comparisons, all we have to do is actually subtract the degrees of freedom to find the degree of freedom for our new test. Well, what you do here is you actually walk through and look at all of these, and anytime you have a p-value less than a significance, less than your alpha, that says if you change that value, then you will get a new chi-squared value that will be statistically significantly different. So most of them are coming up as significant. So what I need to do here is I need to look for the largest of the values. The first thing I notice is that if I let A3 predict B, I get a pretty big jump. A manifest value predicting, that doesn't really make any sense. So I'm going to ignore that one. Again, I get B1 predicting M, doesn't make much sense. And then, now I do notice though, this is curious. A predicting B is a change of 20.925, and B predicting M is the same change. So that's probably an artifact. Which of these makes more sense? Well, M is technically pointing to B already. So I don't really want to have B point back to M. So the A to B probably makes more sense. Now let's scroll down a little further. Let's look at the measurements.
Can you?
Yep. Oh yeah.
Can you do bidirectional paths?
Yep. You can. Not with maximum likelihood though.
Okay.
But you can do it with
It's 4:45.
Two-ways least squares. So that's where you two-step estimation with the least squares. You can actually calculate them.
Can I ask one more question?
Of course. Of course.
So, just in terms of like, reporting things in a paper, is it typical to kind of, so like
let's say the initial model you drew, like that was your hypothesized
Mm-hmm.
model, and then you look and there's other things you can do. So is that normal to then kind of like go through this process and revise the model and say, this is what we thought, this is how we revised it, and this is the final model? That's like kind of the standard progression.
And the if your journal allows more words, so if your journal says, look, 6,000 words or fewer and that's it, you sometimes just have to say, we started with our original model, which was this. After examining the modification indices, we added this.
Yeah. And
it's very brief.
Yeah.
If you've got more space, then you may be able to elaborate one. And one of the articles I'll give you from 2012, Denali's measurement model for free and reduced lens impacts, she actually walks you through each error correlation that she adds, where you go, oh, that makes sense. Oh, that makes sense. You're like, huh? But she actually does include that, which is nice. And we'll take a look at one of those to see how that's done. Again, more often than not, in your dissertation, you'll have lots of room to elaborate all that stuff. When you actually report it in the journal article, not so much so.
So, sorry.
No, don't apologize.
So is CFA like embedded in this? Like,
technically, CFA is what we're doing. Is a CFA is just extracting the measurement model. So just the measurement piece is the CFA.
So I guess I was just wondering, would you run each one individually first? Run the CFA? Like, this is like A. Yep. Does that make sense?
Yep.
This is B. That makes sense.
The only one we couldn't do is B, because there's only 3 indicators.
Okay.
So what you do is you run A, convince yourself A is good. Run M, convince yourself it's good. Then run A and B, and just let them be correlated, but don't try to explain it, and see if everything hangs off of B properly.
Okay.
Okay, sounds good. Fine. All right, so the for the measurement, it's saying, let's see, what does it say on the measurement? This is curious. The measurement is saying A might predict B1. Okay, that's suggesting a cross-loading, though that's not very influential. A3 to B1 makes no sense. In the measurement models, any of them manifest to each other make no sense. And I think the only thing that stands out is M3 to M4. Now, that doesn't really make much sense, but M3 to M4 and M4 to M3. Now, what we'll see is it's probably the same thing if I scroll down 31 and change. Is the same thing as if I allow the errors to correlate. So this is telling me, the first thing I'm getting from my modification indices is that I probably want to add a covariance in there. Before I do anything else, and unless I'm wrong, that 31 is actually my largest modification index. And the way you actually should examine modification indices are go to the largest one first, look a couple around it, and usually they'll make like a scree plot type shape. There'll be 1 or 2 very high, and all the rest will be really low. Your focus is on those large ones. You don't always necessarily want the largest one because it may not be a practical change, but another one might be related to it. And the key is once you change one, I can't use this data. The moment I've changed one, everything else, all the values have to be recalculated again.
Right. When you said that it has to be practical, do you mean that it has to be like meaningful? It has to make
Yep.
sense?
Like the 31.
A can't predict the B1 or whatever. It doesn't make sense.
Well, let's see. That one would probably. This one would probably be okay. The A to B1 would probably be okay, but item A2 to B1 that doesn't make any sense.
Yeah.
Yeah. Yeah.
So we go with the biggest, but also still is.
Yep. And now there are times when you'll actually say, well, I'm going to go with the 3rd biggest because the others make sense, but I can justify that one.